那个真的传到我这比较讲，它应该它什么都看不出。
Alrighty, welcome back to operating systems. So, yeah, midterm didn't turn out too bad, did it? So, everything is returned to you as of some ungodly hour this morning. So, seemed to go all right. Average is like 75 plus a little bit by now. Might also be up to like 76, maybe. I'm not sure. Anyone want to check that? Yeah. 75.9, all right, so close. It might end up going to 76, who knows. So, yeah, wasn't too bad. I was really scared there for a moment because I was watching as they were grading, and like, it was like 30% average, and I was like, oh crap, there's not that many questions left, but it turned out it was like that scheduling question that most people got right, so grades went up, and yeah, it's good. All right, so any concerns about the midterm yet? 76, all right. We've hit the threshold. So yeah, pretty good. All right, today we get to talk about page replacement. So, this is your computer's memory hierarchy. Some of these things might be new. Generally, we're mostly concerned about these top fours or what's in computers most of the, or all the days now. So, at the top, you have your CPU. On it, it has registers. There's not that many of them. They're really, really fast. And, well, there's not that many of them, so the capacity is pretty low. Below that, there's a CPU cache, so like the L1, the L2, and the L3 cache on your CPU. There's more capacity. It's not as fast as registers, but it's faster than anything else. Past that, after you run out of cache, well, there's RAM, or your memory. And that's where our virtual memory system comes into place. And, well, that capacity, most people probably have like 16, 32 gigs of RAM, goes up from there. And then after you run out of memory, well, you have non-volatile memory, probably. So that's like your really fast SSDs that are in most computers nowadays. They're like terabytes, or maybe 512 gigs, something like that. They don't cost as much per gigabyte as RAM, but they're a bit slower. Then past that, you might have like SSDs, like bigger drives, or like thumb drives that have more capacity, but they're slower. Past that, you have those spinning hard drives, like the original iPod that you may or may not have ever seen in your life. And past that, there is tape drives that you have, I guarantee, never seen in your life. How many of you have seen VHS tape in your life? Yeah, it looks like this thing. It has like two things and then spin around and there's like a physical tape on that thing. Yeah, well, that's why they're called tape things. So there's a version of that to store massive amounts of data that's not just a crappy movie from the 90s, I guess. Before that, whenever VHS tapes were used. So they'll store like terabytes and terabytes, and it will be dirt cheap, but it will be insanely slow. And people like Google will use this for like archival storage of things that you likely will never access, but they want to keep it around, and they'll just be like a giant room full of those tapes. And if you want to access it, there's actually a machine that goes and grabs the tapes and like manually loads it to read the data from it. It's really, really slow, but hey, if you want to store like petabytes of data, it's dirt cheap. So you'll probably never see that. So yeah, we probably end on most of our computers around here. All right, any questions about that? So now we need to play some illusion. So if you're designing these systems, the reason we have this giant hierarchy is because we want to hide it from the user. And ideally, we want every level of that to have the speed of the layer above that and the capacity of the layer below that. So RAM's not actually that fast, but if we read a bunch of it and cache it on the CPU, it can look a lot faster than you can physically read RAM from the device. If we read the right things into cache and reuse it over again, and then ideally you want to have the capacity of the layer below it, so you get the best of both worlds. So in that case, if we do something like this, we can actually use more memory across all of our processes than we actually physically have in the machine. So if you only have 8 gigs of RAM and you have, 2 tabs open in Google Chrome and that uses 10 gigs of RAM, well, you might notice that might have happened before and it doesn't crash. It still works, but doesn't really make sense. So what it does is something called demand paging. So we can use memory as a cache for the file system, and also we could map memory pages to system blocks at, like actually on the drive whenever we're reading files. And that way, well, demand paging is that mmap idea we had before. We could kind of just figure out what pages in memory map to what on the disk and not actually read the disk until you actually use them. And then, you access a page, it's referencing a block on the disk, then we read it in from the disk. What could also happen is, well, on the disk, you might run out of physical pages and you don't have anywhere to put it and you don't want to be out of memory. So what you can do is you can make something called swap space on the hard drive itself, and you map that physical page and store it on the hard drive temporarily and free up that block in physical memory, and then you can use it for something else. So this is called swap space. If we've used Windows, I assume most of you use Windows or have used Windows. So in your C drive, there's like something called a page file if you enable hidden files. So that page file is that swap space. So that file will be used whenever you run out of physical memory and you need to start putting pages temporarily on the hard drive. So that's called swap space. And if you run htop on your virtual machine, under the memory thing, there's another thing that says swap space. Likely that'll just be 0 because it's not being used. But if you start using really RAM intensive things, it will start filling up and it will start going slower because, well, it's moving memory to disk and moving it back and forth. So, any questions about that? So, swap space, basically just throwing memory pages to the disk if we actually run out of physical memory. That way, the total memory usage across all your processes can actually be more than the amount of physical RAM you actually have. It's just going to probably be slower. So if you context switch and all of your memory pages are on disk, well, you're going to have to load them from disk back into memory, throw some things out, and it might be really slow. So that process of picking something to throw out and move back to disk to move in another page, well, that's what we get to talk about today. That is called page replacement. So a process's working set should fit in physical memory. What that means is, so the working set is given an amount of time, probably from when you got context switched in to when you got context switched out. The working set is the number of pages your process uses in that amount of time. So if your working set is in physical memory, well, then you don't have to swap to disk. Everything is going to be nice and fast. If your working set is bigger than the amount of physical pages you can fit into memory, then it's probably going to be slow. And the worst case, it can do something called thrashing. And what thrashing is, well, you can't fit all your working set into memory at one time. So you're constantly going to be moving pages to the disk and then loading pages, a different page from the disk back into memory. And then you execute a little more, access a new page, and then you do it again. You move a different page to disk, load another one back in, and things will suddenly get really, really slow because, well, instead of accessing physical RAM directly, you are doing hard drive accesses, which are going to be a lot slower. And this is why sometimes, if you really, really care about performance, because all that is invisible, you don't actually really know unless you're paying attention to your operating system metrics of how much swap space is being used. Your process is just going to go slower and you're not going to really notice it unless someone complains. So if you really care about performance and you're something like Google, well, what you might prefer is you would rather just run out of memory, get an error in your process and have it be dead, and then you'll know oh, well, I need to go buy more RAM. And if you're Google, you probably prefer to just buy more RAM than just randomly have a process that goes slow. Or you just allocate more RAM to your virtual machine or something like that to resolve the issue, and you just get rid of swap entirely. So sometimes people do that now, if you really care about performance. Yep?
word thrashing, is that like because the physical hard drive used to like shake around a little bit, or is that not?
The thrashing?
Yeah. But I make that up.
Yeah, like it probably sounded like hell. So if it was a physical hard drive, whenever it was thrashing, yeah, it would just go like ka-chunk, like it would just kind of sound like it's grinding because it's constantly accessing when it probably shouldn't be. So yeah, likely that's where they come up because, well, as you have noticed in this course, we're not very creative with names. All right, so we get to talk about page replacement algorithms. Should pay attention because this process you will probably do on your final, but it's pretty boring, so we can just go through it. So page replacement, typically you assume that you have a finite amount of pages in physical memory, and your process will just assume one process, you're accessing memory, so you need to bring things in from disk into main memory, and typically you will have more pages you're using than actually fit. So you actually have to make a decision which page to throw out of memory and onto disk in order to load a new one in. So we'll go over 3 algorithms today and talk about 4. So the optimal thing to do would be if you can look into the future and see all the page accesses a process makes, well, ideally you replace the page that won't be used in the longest, so I maximize the amount of hits I get where things are already in physical memory. So that's the optimal thing you can do, but of course you can't implement that because in general you can't predict what a process will do. The next algorithm, which is not really an algorithm, is instead of just making a decision of what page to evict, I just pick a random one and just move that one back to the disk. Turns out it's not that bad. But we don't really have to discuss anything, and how could I evaluate, to tell you on an exam, do the random algorithm. Yeah, that would be fun. All right, the other thing we could do is the old trustworthy thing of first in, first out. So I could just replace the oldest page first, replace it with the new page. Simple to implement. We can all do FIFO, hopefully at this point. Same idea as with scheduling. The last one is least recently used. So instead of looking into the future, I look back into the past. And the idea behind that is I replace the page that hasn't been used in the longest time, because likely if you have just used the page, you will likely reuse the page because while your process is running, you accessed a variable that's on a page, likely you will read or write that variable again, so you're more likely to access the same page. So that's why we do least recently used. So how we evaluate all these things is kind of similar to our scheduling questions, but a bit easier. We assume our physical memory holds, in this case, we'll do 4 pages, and then we access the pages in this following order. So we just give them numbers, so we access them in this order, and then we assume all these pages are initially on disk. We just context switched in this process, and we have to load it from disk into memory. And this is the order we will use for all the examples in the lecture in order to actually compare them with each other. And for this, unlike scheduling where you have to find like average waiting time, average response time, and the number of context switches, for this, it's just number of page faults that happen. So less work to do. So here we'll start off by doing the optimal algorithm, which should maximize the number of page hits we have and minimize the number of page faults we have. So in this case, how I draw all of these things is each box here represents a memory access, and inside of the box is what is currently in physical memory. So initially that box is supposed to be empty, and then above the box I draw in, or I write the number that we're accessing at this step. So in this case, we access page 1 because it is the first one. It is not in memory yet, so we have to read it from disk into memory. So it goes into this box, and because we had to page fault and read it in from disk, I put it in red. And that way at the end, to count the number of page faults or things we had to read in from disk, you just count the number of red numbers. So in this case, this will be fairly boring. So if I access page 2, Well, it's not in memory. I have to read it into memory. In this case, I can fit 4 pages into memory, so I wouldn't just get rid of page 1. That wouldn't make any sense. So I read it in. Now in memory, I have page 1, 2, and in this case, I just read in page 2. Any questions about that? Hopefully fairly straightforward. What should happen if I access page 3? Yeah, page fault loads it into memory. We load it. Next one's going to be the same thing. The first 4 steps are always quite boring. So after step 4, now physical memory is full in this silly example. So page 1, 2, 3, and 4 are currently in physical memory. And my next access is to page 1. What happens in this case? Yeah, it's already in physical memory, so that's great. I don't have to read it from disk, don't have to do anything. So in that case, I just rewrite the same boxes, nothing's in red, because it was essentially a hit. All right, what about page 2? Is that a hit? That is also a hit. All right, now when we access page 5, it is not currently in memory and memory is full. Yep. I dropped 4 in this case. Yep. Yeah, so that's skipping ahead. So in this case, I have to pick one of these to actually evict. If I'm doing the optimal thing, which one should I drop? Well, 4. So why should I drop 4? Well, the optimal thing is to look into the future and see which page isn't going to be used in the longest. So starting at this access, I look into the future. Well, it accesses page 1 next, so I shouldn't get rid of page 1. Then it accesses page 2. I also shouldn't get rid of page 2. Then it accesses page 3, so I shouldn't get rid of page 3. So the only thing that's left to get rid of is page 4. So I get rid of page 4. So in that case, I replace page 4 with page 5. So everyone good on that? All right. Now what happens if I access page 1? Well, that should be a hit because, well, I looked into the future and the next 3 should all be hits. So page 1, that's a hit. Page 2, also a hit because that's still in physical memory. Access page 3, also a hit. Now I access page 4. What should I get rid of now? Yeah, so in this case, as long as I don't get rid of 5, it doesn't matter. So as long as I don't get rid of 5, it's fine. So in this case, I'll just assume I hate 1, so I'll just get rid of 1. So I replace 1 with 4, but of course, we could have replaced 2 or 3 because, well, it's over at that point. So then we access page 5. It's still there because we did the optimal thing. So how many page faults do we have for this optimal algorithm? 6. So you just count the number of red. You can do that on the exam if you want, or circle it, or do whatever you feel like, underline it. Doesn't matter. So 6 page faults. Yep.
What does it mean by like out of physical memory can only hold 4 pages?
So
Doesn't physical memory have like all the like, is that just like
yeah, so this is just so we have to move things in and out of memory. If your whole memory had 4 pages and there are 4 kilobytes, that means you have like 16 kilobytes of memory, which I guess was a thing in the 70s. But yeah, if I asked you to do this now, you have thousands and thousands and millions of pages. So only using Google Chrome will get you to this point of having to move things in and out. So it's just for these questions. Realistically, right, we take millions of pages to finally fill up main memory.
and I see these pages can also talk to the storage.
Yeah.
So like that's why it's getting bigger in physical.
Yeah, these could also, remember when we nmapped like a file, so these could actually represent a file. If these memory pages didn't actually represent a file, they were just part of the program that was running, and we just threw them to disk because we ran out of memory. So they could either represent real files or we just ran out of memory. All right, so 6 page faults. Remember, same sequence optimal, 6 page faults. Same thing, but for FIFO. So we can make this lecture go fast. So can I skip the first 4 steps? All right, so we can speed run this lecture. 1, 2, 3, 4. So we fill it up. Any questions about that? We have our 4 page faults we can't get rid of. All right. So we access page 1. That's a hit, right? Everyone agree? Access page 2. Also a hit. All right, this looks the same as before. So now the difference is we access page 5. So if our algorithm is first in, first out, what do I boot out to load 5 into memory? 1. Because 1 is the first thing I loaded, so that was the first thing in, first thing out, FIFO. So I replace 1 with 5, and that is a page fault. All right, so it turns out I probably made a poor decision, so now I access page 1, which I just threw back onto the disk. Now what should I get rid of for page 1? 2, which will prove also to be a poor decision. So now I access page 2, which I just threw to the disk. That was a poor decision. What do I replace for page 2? 3. Also a poor decision. All right. So now I have this. Now I'm accessing page 3. What do I throw out now? Page 4. So I throw page 4 out, and then you can also see this pattern with first in, first out. You can see there's nice diagonal lines of red numbers. So if it's first in, first out, it'll just look like diagonal lines, so you can really speed run this if you wanted to, because yeah, it's just kind of silly. All right, so now we access page 4. What do I get rid of? Page 5. All right, now I access page 5. What do I get rid of? 1. How many page faults did I have? 10. That was a pretty poor effort on my part, right? So now let's think about this. So this would probably be a lot better if I could fit 5 pages in memory, right? I'd only have 5 page faults in total because I can fit everything. So if I have more physical memory, I have less page faults, right? That makes sense to everyone? So is the opposite true? So if I have less physical memory, I should have more page faults, right? That would make sense. All right, that makes sense. We all agree on that. All right, let's make sure. So we'll do the same thing, but we'll decrease the number of frames or pages we can fit in physical memory from 4 to 3. So same thing, but we can fit less. So we have our first 3 accesses where they have to be page faults. We load it into physical memory. Now we access page 4. What do I throw out? Page 1. Wow, that was a bad decision already. So I throw out page 4, and my next access is to page 1. What do I throw out? Page 2. Another bad decision, so I'm 5 for 5 now. So now we access page 2. It's not in memory. What do I throw out? 3. All right, that brings us up to 6 for 6 for page faults. So yeah, it's not looking good. You guys look like you were right. Now we access page 5. What do I throw out? 4. By waterfall method, it has to be 4, right? So throw out page 4. Now it turns around. So now if I access page 1, it's in memory, so that's a hit. Access page 2. That's a hit. Now I access page 3. What do I have to throw out for page 3? Page 1, right? So now I throw out page 1. Ooh, that was bad. So now I access page 4. What do I have to throw out for page 4? 2. So finally I access page 5, and that's a hit. How many page faults is that? 9. That was better. That was less page faults than before, so seems weird, right? So the solution is, well, if I want to make my program go faster, I just take out some memory and it goes faster. So this has a name. Yeah, we have 9 page faults, so that has a name. It's called Bellide's anomaly, and it says that, contrary to what you believe, if you have more page frames, so you have more memory, that means you have more page faults. And this is a problem specifically for FIFO algorithms. doesn't exist for least recently used or any stack-based algorithms we will see slightly later. And in fact, there was a paper in 2010 that some math people wrote in Greek that I can't understand that summarizes the solution. If you want, you can read the paper. Basically, they concluded that given a FIFO algorithm, I can just construct any arbitrary sequence of page accesses that can cause any page fault ratio I want. So given a page fault ratio, they can come up with a sequence that will cause that ratio. Doesn't matter how many pages there are. So for other algorithms, they behave how you expect. Increasing the number of page frames decreases the number of page faults, so you don't get penalized for having more memory, which is what you would expect. But if you use FIFO, for this specific problem, it has this issue, which is also why, hey, we probably shouldn't use FIFO because this is pretty dumb. Yeah?
Is this a generalization that can be made regardless of what your sequence and like the number of page frames is, or is it just like only in a few circumstances?
Yeah, so this is in specific circumstances. So in general, you don't know how a program behaves, so it could not do this in the real world, but they were like, yeah, we can just construct arbitrary sequences that can do this, but in the real world, you don't control what pages a process accesses, so this may or may not happen in the real world. But you could implement it, but you might run into this where like you have more memory and you have more page faults, and you have to be like, why the hell did that happen? Well, you got unlucky, basically. And why did you get unlucky? Well, a bunch of math people can prove to you that sequences can happen with any page fault ratio. And again, don't ask me about the details of math or anything. I can't do that Greek stuff. It looks like gibberish. I can read C. All right. So now we can do our last one of the day. Wow, we're really speed running this. So this is least recently used. We'll go back up to 4 physical pages. And for all of these, we can use FIFO to break ties. But ties will only happen if we have multiple processes running at the same time. And then, it's essentially like a data race problem, all that fun stuff. So for the purposes of this course, I'll just assume a single process and we don't have to talk about ties. So same situation we had before. We had that weird 3 pages thing, so memory can hold 4 pages. We had the same accesses. Now we're going to use least recently used, which looks backwards into the past. So first 4 accesses are going to be the same no matter what, because we have to load them into memory. Access page 1. Page 1, that's a page hit already in memory. Access page 2, that's a hit already in memory. Now we access page 5. So now I have to choose a page 1, 2, 3, or 4 to throw out of memory and replace it using least recently used. So which one should I throw out? 3. All right, so if I look backwards in the past, I used 2 most recently, so I shouldn't get rid of 2. Before that, I used 1, so I shouldn't get rid of 1. And then after that, I used 4, so I shouldn't get rid of 4. So the last page standing that I kick out is 3. So I replace page 3 with page 5, and this is what it looks like. So it looks like we made a good decision. So if we access page 1, that is a hit. If we access page 2, that is also a hit. Now we access page 3. So now we have to choose something to throw out. What am I going to throw out? 4. So in this case, I will throw out 4 because, well, I can't throw out 2. It was used least recently. I can't throw out 1, and I can't throw out 5. So that leaves 4, sorry. So I have to get rid of 4 for 3. Turns out that was a bad mistake because, well, I couldn't look into the future. Turns out we're accessing page 4 next. So if I access page 4 next, what do I get rid of? 5. So I look at the past. I can't get rid of 1, 2, or 3. That leaves 5, which is a poor decision. Because now I access page 5. Now what do I get rid of? 1, right? So I can't get rid of 4, 3, or 2. So I have to get rid of 1. So I have to get rid of 1, replace it with 5. Now, how many page faults do we have? 8. So optimal was 6. Our first FIFO was 10. Our smaller one was 9. This is 8, slightly better. All right, any questions about that? So that's our algorithms for today. Yay. So, oh, yep. So random depends. So this least recently used typically works really well with like real program usage, because typically if I use a variable x, I'm going to read it soon anyways. So I probably actually, typically if you use something, you'll use it again. So least recently used for most sane programs works pretty well. But if you have a program that just randomly accesses memory just in random places, this isn't going to work very well. And also if you implement it, well, how would I implement something like this? Least recently used? Yeah. Yeah, you could have a counter for each. What about implementing it using linked lists or something like that? So if it's just used, I put it to the front, and then the least recently used will be the thing at the back if I just keep on refreshing it, right? So we could implement this, but those are both kind of slow to do. And well, if the program does random things anyways, I can pick a random number like that. So random decisions are actually pretty fast, so probably faster. So if I try to implement least recently used and say I have a counter for everything, well, that seems like it's kind of impractical to actually implement, because if I read a variable, that means I've accessed it, I've accessed something, right? So I read like a byte, and then suddenly after I read a byte, I have to add a counter to something, which is going to be more than 1 byte. So suddenly things are 8 times slower. Probably not a good idea. Also, if I put a counter on stuff, I'd probably have to search all of the pages in memory, which is also going to be really slow. So turns out if you try to implement least recently used, it's kind of impractical. So if I implement it in hardware and like say I have a specific counter for each page in memory, well, each time I even change or read a single byte, well, I have to essentially save that counter to whatever I'm using to keep track of that page, and that's going to take some time, going to be fairly slow. And then if I want to replace things, well, I have to look at all the timestamps and see what is the oldest timestamp, and then evict that one. That's like ON, so the more memory I have, the slower that's going to be. So I probably don't actually want to do that. And if I implement it in software using linked lists, it has the same problem. So technically, if you're a computer science person, this seems kind of fast because they're like constant operations. So if you do a page reference, so if I access any byte, all I do is move this page to the end of the list move it to the front of the list because it was just used. I'll just assume the most recently used thing is at the beginning of the list. Then eventually it will fade to the back. Then for replacement, that's also constant time because, well, I just pick the thing at the back of the list and that's the oldest page, so I evict that one. But if you actually try to implement that, that means even if I access 1 byte, well, we've all used linked lists before. So to do that constant time operation, I probably need like up to 6 pointer changes of reading and writing pointer values. So it seems kind of bad that I read 1 byte and then I have to read and write 6 pointers. That's probably a bad idea. And also imagine that you have multiple cores running. So if you have one linked list that's keeping track of all the pages, well, would you have a data race for that linked list if you had multiple cores? Yeah, you would have data races for that, so you would have to have a mutex around it, and then it's even going to be even slower than those few pointer updates. So if you actually tried to implement least recently used, it would be way too slow to actually implement, and no one that does it. Yep. Yeah, so you could use an array or something like that, but that still speeds it up. It's still going to pale in comparison to reading a single byte, right? Because this is something I have to do every single time I read even a byte. So if it's something that you do that's more than a byte, it's probably going to be too slow. So what we can do is we do the typical thing we do if we encounter a hard problem. We just change the problem and make it easier. So least recently used is actually kind of an approximation of the optimal algorithm. We can't implement the optimal algorithm, so we use least recently used to kind of approximate that. So just take it one step further. So we can approximate least recently used. So we can actually implement an approximation of the approximation. So there's lots of different ways to approximate least recently used so we can actually implement it. So specifically in this course, we'll be looking at something called the clock algorithm, which will be next lecture. But there's also like least frequently used. So it relaxes it a bit. Instead of the most recently used, it just keeps track of the number of times you reference it, or if you've referenced it at all. There's one with 2 queues that try and speed it up a bit in hardware. There's adaptive replacement caches where you just throw some caches on it. There's all sorts of different strategies. It's kind of like scheduling where there's all different trade-offs you can make. If you make something really complicated, well, it takes longer to run, and sometimes it might make a bad decision anyways, so you may as well have just made a poor decision faster. So, any questions about anything we saw so we can, we sped run. All right, so what we saw today, optimal. So don't use, make sure we maximize the page hits we have. Just replace whatever is used furthest in the future. And we could also just do random page replacement. It actually works surprisingly well in practice because unlike FIFO, which just kind of sucks, it avoids the worst case because, well, it just makes a random decision. Instead of always making a poor decision like FIFO, it can randomly sometimes make a good decision, and it kind of avoids the worst case. If you simulate it, it actually turns out to not be absolutely terrible. FIFO, easy to implement, but has that weird anomaly where, hey, I have more physical memory and I have more page faults. That's not good. And then we round it off with least recently used. Gets closer to optimal, but really expensive to implement, and we will figure out an implementation in the next lecture. So with that, remember, pulling for you.